Learning Measure TV, a science and engineering podcast with emphasis on measurement, brought to you by David Archer and LearningMeasure.com.
Episode 36, Mixing Up the Meter.
Hello, I'm David Archer. I'm the owner of LearningMeasure.com and LearningMeasure.tv. LearningMeasure.com is a subscription-based training website where you have 1 week free when you sign up, and then it's $5 a month for access to all the courses thereafter. I'd like to introduce a new course that was introduced into the course catalog, Measurement 201, Basic AC Measurement. It's part of our series on the ASQ CCT exam. What we talked about last time, if you remember, we talked about noise measurement, mixers, that sort of thing. Well, we're going to talk a little bit now about how you can use electrical signals to measure distance. First of all, I want to talk about what the meter is. Meter is defined as the length of the path of, the meter is the length of the path traveled by light in vacuum during a time interval of 1 over 299,792,458 of a second. So it's basically defining the speed of light when you do that. Now, why would you do that? Well, if you can imagine when you want to send a message. In the old days, let's say you wanted to send a message from, let's say, Europe to the United States. At one point, the only way to do it was through a boat, and that would take months. So it took some speed to transfer the information. Well, later on, they found out they could do it other ways, like radio, which is a lot faster. Well, someone started thinking, well, maybe there's a maximum speed you can transfer information. Maybe there's a speed limit. And of course, that would be Einstein who came up with this. But if there is a speed limit, if someone's sending me something at the speed limit and then I run towards it, I still should see the same speed limit. So if there is really true that there's a maximum speed that you can transfer information, that maximum speed has to be the same for everybody, whether you're moving or not, which is counterintuitive, but it turns out that's the way the universe really works. And we'll get to that in a second. So the meter is defined, again, in how much time a light beam goes in a certain period of time. Well, what is time? How is that defined? Well, time is defined as, or a second is defined as, for SI units, is the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. This definition refers to a cesium atom at rest at the temperature of 0 K. So what is that? Well, what happens in atomic atoms basically have what are called energy levels, right? And there's a ground state, and you can they usually draw little diagrams where they draw, the energy levels as lines. So we're talking about some sort of transition between two energy levels. That's a certain energy, well-defined energy, which is related to the frequency. So there's something called Planck's constant times the frequency is the energy of the transition. So for this particular transition, it's basically that frequency is defined at roughly 9.1 plus stuff gigahertz. Okay, X-band. Something that's wavelength, around like that. So what can we use that directly to measure distance? Well, probably you could. The way it works, the way you make this clock is you have some way, you have some box that shoots out cesium atoms. And then you have some sort of something here that selects out atoms in a particular state. Let's say this excited state or the ground state. I suppose you can go either way. Then that goes into a region where there's some sort of field impinging on the cesium atoms. And then you have the same thing here that selects out the state again. So there's an output that's, maybe it sends atoms in one state this way and different state that way, and there's some sort of detector here. And this would output some sort of voltage, let's say. Well, this RF here, there's some sort of source here, and then there's some sort of, I don't know, antenna or something to put energy into where these cesium atoms in a pre-selected state are. And it's controlled, there's some sort of phase lock loop circuit in here that adjusts the frequency of this radiation until you get to just the right frequency where all the atoms in this state transition to the state you want, and that happens at that well-defined frequency. So now you have this 9.1 something or other gigahertz frequency source that's very accurate. Well, what can you do with that? I mean, this was I'm kind of skimming through this a little fast, but okay, now that you have a source that's of a known frequency, what can you do with it? Well, back in the very old days, there used to be a device called a slotted line. Here's an example of one. A slotted line was a device that's hardly used anymore. It was basically used to measure reflection coefficient. You could get magnitude and phase out of it. And this is how it worked. You had some sort of transmission line, maybe some sort of coax or something, and you had some sort of source. And then you had, at the other end, and this would have to be some sort of uniform transmission line. It has to be very uniform for this to work. And then at the other end, you'd put something on the end, like a transmission, or like a termination, but we're going to put something like a short. Okay, a short is just a piece of metal that reflects back the energy. So let's say you have we talked about traveling waves in a previous episode. So let's say what's coming out of what's going through this way is cosine omega t plus kx. Okay. Well, this wave comes down, hits the short, some of it comes back. Well, in order for the field to be, because this is metal, the voltage here at that point has to be 0. So what has to come back here has to cancel that. And if we call this x0, let's call that x equals 0 just to make things easy, then the total voltage, which is, well, something like this going this way, must add something going this way to get 0 here. Well, it turns out that's minus v cosine omega t minus kx. So this represents a wave going that way. Okay. So what you do now is you stick some little probe in here, some sort of pickup probe that goes off to some meter of some sort. And you move this probe back and forth in here, and you hope the probe doesn't interfere with it too much. And as you move this probe back and forth, you'll see something that looks like this. Well, what is that? Well, if you look at this equation up here, we'll come back to this in a minute. This is v times cosine omega t plus kx minus cosine omega t minus kx. Well, you can apply a trig identity to this. It turns out this is v times sine omega t times sine of kx. Oh, and there's a factor of 2 in here. Okay, so you got something that's a function of time, which is just basically the frequency that's coming out of here. And then you got this thing that represents an amplitude as function of distance. Well, if you look at this sign, when kx, there's a null, there's 0, appears whenever kx equals n pi. So there's a whole bunch of zeros. Well, there's my phone going off, but I'm going to let it go. So now what is k? Well, k equals 2 pi f over c, which is the speed of light. So we can put that in there. We've got 2 pi f over c equals nx. Okay. Or sorry, n pi x. Solving for x, you end up with, now let's make this go away, x equals cn over 2f. Right, the pi's cancel. So this is where that is. But what is this c over f? Well, that's lambda, so it's also equals lambda over 2n. So what you have is every half wavelength there's a null. So as you move this back and forth, you can figure out what this distance is by looking at the distance between two nulls. And you've effectively created something that you could actually define a length with. Problem is, these wavelengths are like this big, so this is like this kind of distance. And if you look at what the nulls look like, they're kind of mushy. So that means they're kind of hard to tell exactly where the null is. So there's a lot of uncertainty that's going to be using something like a slotted line to measure distance. But you could do that. You could create a traceability for distance measuring through a slotted line. You wouldn't want to. What you want to do is use higher frequencies, shorter wavelengths. And really the wavelengths you want to use, in most cases, are going to be light. So what would be the light analog to this? Well, this is what it would be. You have some laser. This is will give you a source just like at RF. And then you sort of squirt out the light beam and you put it in a half silvered mirror. Well, okay, anyway, so what happens is 50% of the light goes through and 50% of the light goes this way. Now, you put a retroreflector here. So some comes in, comes out, goes back down, comes out. Some of it goes this way, some of it goes back this way, but we don't care about that. We don't use that. And then we put another retroreflector here. So light comes in, comes around, comes back. Half of it goes through, don't care. The rest of it comes down this way. Well, you basically have the exact same thing as in a way, of the slotted line. If you look this way, with your eyeball, and you're going to see, let's say you move this back and forth. These things are going to move in and out of phase, and you'll see nulls. again, every half wavelength. Now the half wavelengths are a lot smaller now, so you get a much more precise distance. You also could move this mirror back and forth. And you could then you could get measured distance that way. Like you could put it at a null, you know, find a position that's a null, and move some reference mark there. And then move it, count the number of nulls to a different place, like let's say 1 meter away, which you know what it might be, on a meter bar or something, and you count the number of nulls. You can figure out how long something is. Now, this setup also has had a different use, but this will get you. It's called an interferometer. In fact, it's called a Michelson interferometer. Before we get to that, what this laser gives a frequency. For this to work, we need to know what the frequency of the laser is. Well, how do we know what the frequency of the laser is? We only know what the frequency of this RF thing is, that the cesium standard is. So we have some sort of source. Let's give you this precision cesium standard frequency. Well, we know how to do one thing we've talked about in previous episode. You could split the signal, put it into a mixer, put it into basically a high-pass filter, and what you get something out is you got some F here, you get 2F out here, frequency doubler. And you can keep doing that to some extent, and there are devices analogous to this. So you could build a chain of like frequency doublers and eventually can lock to a laser with something like a phase lock loop in a series of steps all the way up to the light frequency. And this has actually been done in the past, and we can talk about that in a future episode. In fact, I want to. So, but anyway, in principle, you could start out with a cesium frequency standard, multiply it up to something like a laser frequency. You could control the laser frequency to be traceable directly back to the cesium standard, which gives you the definition of the second, or the hertz even, in this case frequency. And then you have a directly traceable back to frequency realization of the meter. Now, I had said at the beginning that one of the things that Einstein just what's called a postulate, is that the speed of light is the same for all observers. Well, in scientific postulates, you don't prove postulates. What you do is you do experiments to see if they're consistent with observations. You can never actually prove them, but you can only disprove them. And one of the thoughts of how they might disprove it was well, consider light. If light's really going at the speed limit that you can transfer information, if we're sitting here on, let's say here's the sun, and we're here on the Earth, and we're orbiting around the sun. Okay, we're going some direction. And the sun is moving around the center of the galaxy, and the galaxies are moving relative to each other. So certainly the Earth's velocity is not zero, you know, in any stretch of the imagination. So it's moving. So if the speed of light is different for different observers, not the same for all observers, you'd think if you looked in this direction, you'd measure this one speed of light, and if you looked in this direction, you'd measure a different speed of light. Well, if you think about what this thing's doing, you're counting on the speed of light being the same in both of these directions. And so if it may be for one particular direction for a period of time, but as the Earth rotates on its axis and rotates around the sun and rotates around the galaxy, as with time, you would think you would see nulls shifting here because you're constantly changing the direction you're looking. So it's one time you're moving this way and light's moving this way, so you'd think it would be a different speed. Whereas a little while later, you're moving this way. Okay, well, this experiment is one of the colossal failures that helped prove that Einstein was right. Because they never were able to measure, regardless of what direction you pointed this thing, any difference in the speed of light in any direction. Now there's a whole bunch of other types of measurements that verify this, and this is the basis for why you set the meter now in terms of the second and defining the speed of light. Because it is really, so far, been borne out with experiments, the speed of light is indeed independent of the observer. So, well, we now have a way to get distance from frequency. What are some of the funny things you can measure when you have that? That's what I want to talk about next time. All right, that's all I want to talk about today. We'll see you next time.
Just wanted to mention that next week I'm going to the Measurement Science Conference, and if anybody out there that watches the podcast is going to be there, I'd like to meet you. If anybody out there would want to be interviewed, I'll bring my camera and we'll set up an interview if you're interested. Anyway, as always, if you have any questions that you want to ask me about, send me an email at questions@learningmeasure.tv. If you have any suggestions for the podcast, send me an email at suggestions@learningmeasure.tv. And if you want to get on the podcast, send me an email at vendors@learningmeasure.tv. Okay, hope to see you at the conference. Bye-bye.